Hi guys, this is section 9.6 and this is on logarithmic scales. I have a journal choice for you, and this section of the book I found very interesting. When I taught it for the first time, I was kind of stressed out, to be honest, because there's a lot of science going on and I wasn't really understanding all the details about it. The math in this section is not easy at all. I just really wanted to make sure that I understood the science behind it. So if you have any of the science questions, I can try to answer them, but the bulk of the notes is going to talk about the math applications, and I think the math part will be pretty easy for you. Okay, scales you may have heard of. Logarithmic scales are used when all the measures of an attribute are positive and they cover a wide range of values from small to very large. Okay, this makes sense because logarithms are talking about exponents, and if you have exponential growth, things get very large very quickly or very small very quickly. So we use this logarithmic scale whenever you have some exponential growth pattern or exponential decay pattern. The two logarithmic scales that are the most famous are the decibel scale and the Richter scale. And I think most of you have heard of the Richter scale, maybe not the decibel scale. But we're going to talk about both of those today, and those are the only two we're going to be talking about today. The one that was most confusing to me is the decibel scale. The reason being is because I don't have my mom was a music teacher and my dad is a science teacher, but I still don't have a very clear understanding on what a decibel is. And I think it's the unit that confuses me. It is based on watts, and watts is a measure of power, so I guess we're talking about the power of the sound. Kind of like volume, I guess. But really, sound intensity is what they're talking about. How intense is the sound? Okay. Well, the range of sounds human can hear is between 10 to the negative 12 and 10 squared. And because that range is so large, what we're going to do is they go by multiples of 10, and then the exponents. That's what we're going to talk about, is the exponent of the base 10. Here is a formula you will need to jot down because you are going to use this in your homework when we go over the problems. This is relating decibels to newtons. Okay, so this is how intense some, I don't see, and this is what's confusing me, some Newton value of sound is. I don't know how you measure sound in newtons. That's confusing to me, but the math part is not. So this formula is what you're going to be looking for, and this is if you're looking for relative intensity for D. If they're asking you for relative intensity, you're going to be using this formula, or if they're talking about decibels, and if they give you something in newtons, or they give you something in watts per meter squared, which is also what a newton is, then you're going to go to this formula most likely. Okay? Here's the chart, and this does make sense to me, and I do find this interesting. Basically, because the newtons are so widespread when you look at them, it is not very handy to refer to different noise levels as like something as 10 to the first watts per square meter, or newtons even, 10 to the negative 7th newtons. This is not convenience. For some reason, humans like to deal with smaller numbers that we encounter in our everyday lives. Exponents aren't very happy for us, so we like some regular numbers. So what we're doing is we're going to transfer this geometric sequence of numbers that I'm multiplying by 10 each time to something arithmetic, which I'm adding 10 each time. So we're transferring these bigger numbers into something more manageable. Okay? Now, what happens is that whenever there is an increase of 10, so something is getting plus 10 on the decibel sides, we're going to be multiplying by 10 on the newton side. So something was plus 20, like from 20 to 40. I'm not adding 200 here. I'm multiplying by 10 squared. The 20 becomes here, plus 20, 10 squared, 100. Okay, here is, I just find this kind of interesting, all these things we can hear, how far spread apart that is. But here is another thing you want to jot down. If they are just asking you to compare sound intensity to newtons, this is what you need to know. An increase of n decibels multiplies the sound intensity by 10 to the n over 10. And that's what I was talking about. If there was an increase of 20 decibels, then you take 20 divided by 10, which is 2, and it's 10 squared, 100. All right, so let's look at number 1 here. Music is played at 125 decibels is how many times as intense as music played at 105 decibels. Well, what is the difference? I will take 125 minus 105, and the difference is 20 decibels. Let's go back to our chart. 20 decibels, so it was from 125 to what? I missed it. Oh, 105. 105, which is right here, to 125, so we're going up 20. So here we're going up 10 to the squared. Basically, you're going to take this 20, 10 to the 20 over 10, which is 10 squared, or 100 times as intense. If the difference was 30, you would take 30 over 10 and be 10 to the third, 1,000 times as intense. Okay, I think that should make sense to most of you. There's another example in your book on page 616. The difference actually is 15. It doesn't have to be a whole number. So then they have 10 to the 15 over 10, which is 10 to the 1.5, which works out to be about 32 times as intense. Okay, so it doesn't have to work out nicely. You could have a fraction or decimal as an exponent here. Okay, question 2 is talking about relative intensity. You should have written down already a formula that deals with relative intensity. Okay, we have it right here. Maybe. There it is. D equals 10 log n over 10 to the negative 12. So I'm going to write that down. This is a little touchy today. Let's try again. There we go. D equals 10. Now this is 10 times the log of the newtons over 10 to the negative 12th. Now, remember what the base here is of this logarithm. Because it doesn't say what the base is, it can be assumed 10. They're talking about the common logarithm, which has base 10. We're looking for the relative intensity in decibels, so this is what we are looking for, this D value. And the newtons we are talking about is 3.16 times 10 to the negative 8. So D equals 10 log 3.16 times 10 to the negative 8. I'm going to grab my calculator. Okay, there are a couple things that I did here first. I did the parentheses first, so then I went to 10 log of 31,600. Okay, here's where it gets a little tricky, especially if you're using an Inspire. When you type this in your calculator, you're going to type it in just as you see it. 10 log. Now, your Inspire is going to ask for the base. Everybody else with the 84s is not. You're going to just type it in as you see it. 84s, this is very easy to type in. 10 log 31,600, you're going to get an answer. Inspire people, you're going to type in 10 log 10, 31,600, and you need to put a decimal there because it's not going to give you a decimal approximation if you don't. And the value I got was 44.9969. We are going to go ahead and approximate that to the nearest decibel. So we're going to go ahead and say 45 decibels. Okay, how about this one? A very loud rock band plays at a relative intensity of 125 decibels. What is the sound intensity? This time they're telling me the decibels. We're going to be looking for the newtons. So we're going to use the same formula again here. D equals 10 log n over 10 to the negative 12. Okay, plug in what we're given. The 125 decibels is right here. equals 10 log n over 10 to the negative 12. Be careful here. We are looking for n, so we're going to go ahead and try to get this n by itself. The first thing we're going to do is we're going to move this 10 by dividing both sides by 10. So I have 12.5 is log n over 10 to the negative 12. This is when I wish you guys were with me instead of watching this. What do you do here? It is very hard to get n by itself. Do I divide both sides by log? No, that's ridiculous. What I can do, if I have a logarithm, I'm confused what to do, change it to look a way that you're more familiar with. Remember, this is a log base 10. So let's change it. 10 to the 12.5 equals n over 10 to the negative 12. Now I know what to do. I got to get n by itself, so I multiply both sides by 10 to the negative 12 times 10 to the negative 12. And I get n equals, well, I get 10 to like the 0.5. I'll go ahead and get a decimal approximation for that. Which is about 3.16. We were talking about n, which is newtons. Okay, the algebra is a little tricky. I think you can handle it. I do think this is where you'll get lost. If you get lost anywhere, you'll divide by 10 and then you'll be like, oh my gosh, how did I get this n by itself? Change it to that exponential form and then you'll know what to do. Okay, let's talk about Richter's scale. You've heard this all the time. Richter's scale is used to measure the strength of earthquakes. It is also a logarithmic scale and it's designed by this guy. Here's how it works. A value x on the Richter scale corresponds to a measured force or amplitude of k times 10 to the x, where the constant k depends on the units being used to measure the quake. Each increase of 1 on the Richter scale corresponds to multiplying by 10 once again. So here is what we're dealing with. This is how it is laid out here. Every step would be like times 10, times 10, times 10, yada, yada, yada. Okay? This is not comparing two units so much, but it's talking about each number is 10 times as strong. So if you go from here times here is times 10 times 10, it's 100 times as strong from 5 to 7. Okay? On May 12, 2008, that place in China had that horrible earthquake, and it was 7.9 on the Richter scale. And then there was the tsunami. Okay, the tsunami that happened in 2004 was triggered by a 9.3 on the Richter scale. That's really big. How many times greater was it? Well, what you're going to do is you're going to subtract here. You're going to take 9.3 minus 7.9. And when you do that, you're going to get how many, you're getting that exponent again, okay? That will be to the base 10. So I get 1.4 times here. So it's going to be 10 to the 1.4 times is great. Well, here, let's just go through their steps. I forgot this was here. The amplitude of the 2008 quake was k times 10 to the 7.9. The other one was k times 10 to the 9.3. You would divide to compare the amplitudes. So I'm going to put the 9.3 on top because they're going to keep it positive. And that will be 10 to the 1.4. Okay? I don't divide. I just subtract. It will be the same thing here. When you're done, you're going to take the 10 to that 1.4 and you will get, well, what did I get? 25.1 or 1.2 it looks like. So it had about 25 times the force of the 2008 quake. Okay. Here's where you might have some hiccups. Okay, subtract. I put the 9.3 on top to keep this positive. If I would have put the 7.9 there, I would have had 10 to the negative 1.4. That's okay, but in that case, I would say that the other quake was that much weaker than the other one. You need to be reflective over which quake was stronger, so you need to make sure that you give your results in a way that makes sense. Okay, so here's what we're going to be looking at. You're going to be subtracting the difference when you're comparing, subtracting the difference, well, subtracting there is a little bit redundant, subtracting the, what are those, Richters? Subtract the Richter values, I'll just put that. And then you'll take 10 to that difference, and that'll tell you the difference in the strength, if that makes sense. Okay, here's your homework. We'll be talking about that in class. The math isn't hard. The science to me is a little confusing. I'm sure a lot of you will understand it much better than me. They're going to throw another formula at you in the middle here, but basically you really need to make sure you just figure out what goes into what part of the formula, and then use what you know about logarithms to find the missing values. Okay? We will work on this tomorrow.